In today's lecture, we are going to see a very important concept of inertia tensor in case of mechanics of rigid bodies. But actually, to develop the concept of inertia tensor or moment of inertia tensor, first of all, you have to see how we can define the angular momentum of a rigid body rotating about a fixed point or rotating about an axis. Because inertia tensor, the idea of inertia tensor just comes out as a byproduct of the expression for angular momentum of a rigid body. Okay. So actually there will be two parts of this lecture. First of all, we will see the expression for angular momentum of a rigid body, and after that you will see the final expression for angular momentum will provide the idea of moment of inertia tensor and also the product of inertia in case of motion of rigid body. Okay, so let us see this figure. Actually, in this figure I have shown a rigid body. This is a rigid body, you can assume of any shape and size. Okay, and we have also assumed that this body is rotating about a fixed point, let us say O, which is fixed in the body. It is not outside of the body, but point O about which the body is rotating, that is inside the body. Actually, when you say that the body is rotating about a fixed point O inside the body, it means definitely there will be an instantaneous axis. Okay, let us see this figure that we assume that this is an instantaneous axis which passes through the fixed point O. Okay, this is instantaneous axis, and this body is rotating about this instantaneous axis. Okay, now at any instant of time the body will be rotating with, let us say, angular velocity omega, and this angular velocity will be definitely, since it is an axial vector, so this angular velocity omega is directed in the direction of the instantaneous axis through the point O. So I have shown this omega, which is angular velocity of the body along in the direction of instantaneous axis. Okay. One thing definitely you have studied in your lower classes, that in case of rotation of a rigid body, each and every particle of the body has same angular velocity, which is equal to angular velocity of the body. Angular velocity is not different for different particles. The distance of different particles from the axis of rotation may be different, but angular velocity remains same. This is a very important fact which you have definitely studied in your lower classes. So whenever you will talk about any particular particle of this body, then the angular velocity of that very particle will be also equal to omega, if omega is the angular velocity of the body. But what about the linear velocity of a particle? Definitely, linear velocity of a particle, of different particles are different, not same. It depends on the location of the particle from the axis of rotation. Okay. So for calculation, I have assumed a particle located at this point P, and let us say this is an ith particle. We consider that this rigid body consists of a large number of particles, say n. N is the total number of particles contained in this body. Okay. For a time being, we have considered that this rigid body is composed of discrete distribution of point masses or particles. This is just for sake of simplicity or for the convenience of calculation. Okay. And among those n particles, I have considered here one of the particles, that is ith particle, whose position vector with respect to this fixed point O I have shown is Ri. This Ri is the position vector of this ith particle. Okay. Now, as you have seen, omega is the angular velocity of the body. So the angular velocity of this ith particle will be also equal to omega, And if its linear velocity is vi, it means vi is the linear velocity of ith particle, then you know how this vi is defined. Vi is simply equal to the vector product of omega and the position vector Ri. So Vi is given as omega cross Ri. And you can see, since for different particles this Ri is different, and therefore this linear velocity is also different. Okay. Now we consider a coordinate system, as you can see in this figure. This is Ox, Y, Z. Actually, this is a body set of coordinate axes. Actually, in my previous lectures, I have assumed the body set of coordinate axes by the primed symbol O dash, X dash, Y dash, Z dash. Because there was also a space set of coordinate. We have denoted a space set of coordinate as unprimed set of coordinate and body set of coordinate as primed. Since here we have to assume only one body set of coordinate axes, there is no need to consider any space set of axes. So I have not written the primed symbol. So Ox, Y, Z, this coordinate system is actually a body set of coordinate axes, and its axes are attached to this rigid body. Okay. Now actually I have written these facts as you can see it here. What I have explained, I have written it. Vi, which is linear velocity of the ith particle, that is equal to omega cross Ri. Okay. And Oxyz be the body set of axes fixed in the body. Now, if you consider that omega x, omega y, and omega z are the components of angular velocity omega along x, y, z axis, then this omega will be written as the vector sum of all these three components. So omega is expressed as omega xi plus omega yj plus omega zk. You know it. Okay. Now, our aim is to find or define the angular velocity of this rigid body about the fixed point O, which is fixed in the body. But as you know, body is composed of a large number of discrete particles. Our assumption is, for the time being, that this body is composed of n discrete particles. So if your aim is to find the angular momentum of the body, what you will do? You will find the angular momenta of every particle, and then you will add those angular momenta vectorially to get the angular momentum of the rigid body. So let us now define the angular momentum of the ith particle. Angular momentum is simply the moment of momentum. It means moment of linear momentum. R cross P. This is a well-known formula of classical mechanics for angular momentum. So L is equal to vector product of position vector R and linear momentum P. So if you are talking about the angular momentum of ith particle, which is Li, then this Li is defined as Ri cross Pi. Here Ri is the position vector of ith particle and Pi is its linear momentum. But linear momentum is simply the product of mass and linear velocity. So instead of this Pi, you can write MIVI, where Mi is mass of the ith particle. Okay? But you have defined this Vi in this way. This is omega cross Ri. So in this expression for Li, you can replace this Vi by the expression omega cross Ri. So Li is actually equal to mi cross omega cross ri. Okay. But if now we will define the angular momentum of the entire body about the point O, what you will do? You will take the summation of angular momenta of all the particles. So, if L denotes the angular momentum of entire body, or you can say the given rigid body about the point O, then this will be equal to summation over I from 1 to n Li. Okay. But Li, we have seen this is equal to this much, this is Ri cross Mi Vi. And Vi, you can replace this Vi by this expression omega cross Ri, as you can see it here. Okay. So I have written it. Now, definitely you have an idea of vector triple product. You know, if A, B and C are three vectors, then vector triple product is denoted as A cross P cross C, and it is defined as A dot C times B minus A dot B times C. So, by the use of this formula of vector triple product, you can simplify this product Ri cross omega cross Ri. Okay, here at the place of vector A there is Ri, at the place of B there is omega, and at the place of C there is again Ri. So utilizing this formula for vector triple product, you can write L is equal to summation over I mi Ri dot Ri times omega minus Ri dot omega times Ri. Okay. Now, you know Ri dot Ri, this will be simply Ri square. Okay. So, L is given as summation over I mi Ri square omega minus Ri dot omega times Ri. Okay. You can see, if this second term is not present here, then we can say that this L vector will be directed in direction of omega. In lower classes, we have studied that the angular momentum vector is in the direction of angular velocity, but it is not strictly correct. It will be a special case. It may happen in a particular situation, but in general, you can see from this equation that L is not directed in the direction of omega. In some specific condition, when this term will vanish, this second term, then you can say that L will be directed in the direction of omega. So never state such a flat statement that L is always in the direction of omega. This is a wrong statement. This may be true only in a specific condition, but in general it is not true. In general, you can say that L is not in the direction of omega. And it is obvious from this equation 1 due to the presence of this second vector term. Okay. Now, our aim is to find this L. L is a vector, so we have to find its magnitude and direction both. So, let us try to find this L by decomposing it into its components. If you know components of a vector, you can easily find the given vector by vector addition of the components. Now, if Lx, Ly and Lz be the x, y and z components of vector L, then you can write L is equal to this much, that is, this is Lxi plus Lyj plus Lzk. And if you can see the figure, I have assumed that this point P is located at a point whose coordinates are xi, yi, zi. Okay. Then this position vector Ri can be expressed in terms of these coordinates, and you can write Ri equal to xii plus yij plus zik. Okay. And you have also seen what is the expression for omega. You have seen here omega is this much. So the scalar product of Ri and omega which exists in the expression of L will be this much. You know, a scalar product is found by simply taking the product of the corresponding components and summing over. Okay. So Ri dot omega, this is equal to this much, and you know well it. Okay. Now let us substitute this value of Ri dot omega here in equation 1 and simplify the result. So you can see at the place of L, now you can write Lxi plus Lyj plus Lzk. Okay, and that is equal to summation over I mi Ri square times omega. But at the place of omega, now you can write omega xi plus omega yj plus omega zk. Okay, and now see Ri dot omega, this is equal to this much. You have seen just now. This is xi omega x plus yi omega y plus zi omega z. And times Ri, you can see, but Ri is equal to this much. So let us substitute xii plus yij plus zik at the place of Ri. Now we will simplify the RHS of this result a little bit to obtain the values of Lx, Ly and Lz. You can simplify it very easily. You can see. First of all, think. We will associate all those terms in which I is a common factor. The unit vector I is present in several terms, and you have to collect all those terms which are associated with I. Okay, so you can see the first term associated with I is Ri square omega x. So I have written it here. Then you can take the product of these three terms xi omega x, yi omega y, zi omega z with this xii. When you will take the product with this, your result will be xi square omega x after multiplication of first term. Then the second term will be xi yi omega y. You can see. Third term will be xi times zi times omega z. You can see. And I will be a common factor. Okay. Similarly, now you have to associate all those terms in which j is a common factor. So you can see when you will take mi square omega yj. So the first term is summation over I mi Ri square omega y. Then take the product of these sum of three terms by this omega ij. And after taking this product, you will get this much. Okay? And j will be a common factor. Similarly, we take k as a common factor and the remaining terms will be like this. You can do it. Okay? Now, we will simplify a little bit too. You can see it here. Now, as you can see in this first row, the first term contains omega x, and this second term inside this small bracket is also contains omega x. So associate these two terms. After associating these two terms, you can see that this is equal to omega x. Omega x has been written outside of the sign of summation because it has no relation with this sign of summation, because summation is implied for I, that is for number of particles, and omega x is independent of the number of particles. Okay. So the first term will be summation over I mi Ri square minus xi square. Okay. Then the second term will be minus omega y summation over I mi xi yi. You can see. And third term will be minus omega z summation over I mi xi zi. Okay. Now see the terms in this second row. In this second row, we can associate this first term Ri square omega y and yi square omega y. So here, this has been written it here. Okay, and the remaining terms are minus omega x summation over I m I y I x I minus omega z summation over I m I y I z I, and j will be a common factor. Similarly, the third term has been written. Now let us see Lxi plus Lyj, okay, and plus Lzk. This is equal to this much. And you know, if two vectors are equal, definitely the two vectors will be equal only when the x component of first vector is equal to the x component of second vector. Y component of first vector is equal to y component of the second vector, and the z component of first vector is equal to z component of the third vector. Only two vectors can be equal. Since here the vector in LHS, which is Lxi plus Lyj plus Lzk, is equal to vector in this RHS. So definitely you can equate the x, y and z component of these two vectors. So see, Lx, which is x component of the vector in LHS, what is the x component of vector in RHS? Can you say? You can easily say the coefficient of unit vector I is the x component of the vector in RHS. So Lx will be equal to what? That will be omega x times summation over I mi times ri square minus xi square. Okay? Minus omega y summation over I mi times xi times yi, and minus omega z summation over I mi times xi zi. And in the similar manner you can equate Ly and Lz. So I am not turning the page. You can see, you can do this algebra easily, and you can see that Lx then is given as omega x times summation over I mi times ri square minus xi square, and minus omega y times summation over I mi xi yi minus omega z summation over I mi xi zi. Similarly, you can find the expression for Ly and Lz, which I have written in equation 2b and 2c. You can note down these things and you can do this algebra easily. Okay? Now, actually the three equations 2a, 2b and 2c, we can write these three equations in a most convenient form. You can see I have written these three equations in this particular manner. Lx is written as Ixx omega x. You can see here this Ixx has been written at the place of omega x times summation over I mi times ri square minus xi square. Okay, that has been written as by the symbol Ixx. Let us wait. What is this Ixx? Let us wait. We will see what is this Ixx. Okay. Similarly, in the second term, this summation over I mi xi with negative sign has been written as by the symbol Ixy. Ixy represents what? Minus summation over I mi xi yi. Okay. So the second term is Ixy times omega y. And in the third term, minus summation over I mi xi zi has been written by the symbol Ixz. Okay. And the remaining factor is omega z. So in this way you can write Lx equal to this much. Similarly, the expression for Ly and Lz have been written here. You can see Ly is written as Iyx. This is Yx omega x plus Iyy times omega y plus Iyz times omega z. Lz is written as Izx times omega x plus Izy times omega y plus Izz times omega z. As I have told you earlier, that this Ixx, this has been written at the place of summation over I mi times ri square minus xi square. And since vector ri is equal to xi I plus yij plus zik, you know it, okay? Can you say what will be the modulus of this vector Ri? That will be simply a square root of xi square plus yi square plus zi square. So you can easily say that this Ri square is simply equal to xi square plus yi square plus zi square. Okay? So if your aim is to express this quantity Ri square minus xi square in different form, you can see from this result that Ri square minus xi square, this is equal to yi square plus zi square. Okay? So instead of Ri square minus xi square, you can write this yi square plus zi square. Okay? You can write. In the similar manner, you can define Iyy and Izz. As you can see, Iyy is equal to summation over I mi ri square minus y square. And by the same reasoning, you can replace this ri square minus y square by xi square plus zi square. And Izz, this is equal to summation over I mi times ri square minus zi square. And that's equal to summation over I mi times xi square plus yi square. Okay? And as you have seen earlier, this Ixy has been written at the place of minus summation over I mixi times yi. But this, see, the expression for Iyx, this is summation of minus summation over I miyx. But there is no difference between the product of xiyi and yixi. So I have written it here that this Ixy is also equal to Iyx. And in the similar manner, you can see Ixz is defined as minus summation over I mixi, and that is also equal to Izx. And Iyz is equal to minus summation over I miyizi, and that is also equal to Izy. Okay? Actually, these three quantities, Ixx, Iyy and Izz, all these three quantities are known as moment of inertia of the body about x-axis, y-axis and z-axis. It means, what is this Ixx, which is defined here in this equation 4a? Actually, this Ixx is the moment of inertia of this rigid body about x-axis. And similarly, you can say that Iyy, this is moment of inertia of this body about y-axis. Okay? And Izz, this is moment of inertia of the same body about z-axis. Okay? So these are the moment of inertia of the body about the x, y and z axis, you can see. But what is these Ixy, Ixz and Iyz? What are these? And Ixy is also equal to Iyx. Actually, all these six quantities, there are six quantities, although due to this symmetry, there are only three values, but the total number of quantities is 6. Actually, these 6 quantities are known as product of inertia. These are called product of inertia. You can say Ixy or Iyx. Ixz or Izx, Iyz or Izy. All these 6 quantities are known as products of inertia of the body about the respective planes. It means when you write the symbol Ixy and define it in this manner as I have defined in equation 5a, then it is called product of inertia of the body about xy plane, about xy plane. And when you write Ixz defined in this equation 5b, then it is the product of inertia of the body about the xz plane. Okay, and Iyz or Izy, this is product of inertia of the body about yz plane. So one thing is very remarkable here. You can see moment of inertia of the body is defined about an axis, but the product of inertia of the body is defined not about an axis but about a plane, with respect to a plane. Have you understand? This is very simple concept. Definitely you are getting the things. Okay. Now actually I have written the components of the angular momentum vector L in this equation 3. You can see Lx, Ly and Lz have been defined. Actually these components Lx, Ly and Lz, which have been expressed in terms of inertia, moment of inertia and product of inertia, actually all these equations can be written in compact form by a single equation. A single equation can give you all those 3 equations. And how you can write that single equation? If L alpha is the component of the angular momentum vector, then this you can write this L alpha in this manner. This is summation over beta I alpha beta omega beta. Here alpha and beta stand for x, y and z. For example, if you take alpha equal to x, then you have to take beta equal to y. Beta equal to y and z. You can't take x because you have taken alpha equal to x. So what will be this equation? This will be Lx equal to, okay, and summation is implied for beta. Mark it. This is for beta, and beta here when you take alpha x, then you have to take beta y and z. So the first term will be I x and beta is y, I x y. Okay. No, sorry. You have to also take beta equal to x, y, and z both. So this is I x x. Okay, and omega beta. Beta has been also taken x. So this is I x x omega x. Okay, plus. Now the second term will be x is fixed, alpha is fixed. So this will be I x and beta. Now you have to take beta equal to y. So this is I x y. And omega y, okay, plus. Now I alpha is fixed, this is x, and you have to take beta now equal to z. So this is z and this is omega z. You can see this is the expression for Lx. In the similar manner, you can find the expression for Ly and Lz too. You can easily find it. Okay. So this single equation defined in equation 6 actually defines all the 3 components of the angular momentum vector, and all the moment of inertia and the product of inertia of the body about the different axes and different planes. Okay. Actually, this equation which I have written here, these are actually the linear equations you can see. And for convenience or for the sake of simplicity, this equation can be easily written in matrix form, in matrix notation. So how you will write this equation 3 in matrix notation? You can see it here. This is the matrix form of that very equation. You can see in LHS I have written a column matrix, or you can say column vector, column matrix or column vector. And that column matrix is Lx, Ly, Lz, which are actually the x, y and z component of angular momentum vector. Okay? And in RHS, at the place of omega, there is actually another column vector or column matrix, omega x, omega y, omega z. And this column vector has been operated by a 3 by 3 matrix here. This is a 3 by 3 square matrix. And its elements has been written Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz. You can check if your aim is to find Lx, how you will find, you are knowing it. This will be Ixx times omega x plus Ixy times omega y. I hope you have an idea of matrix multiplication. Definitely you know matrix multiplication. And plus Ixz times omega z. And the similar manner you can find Ly, Lz. So this is a most suitable notation or most suitable form to express that very equation. Okay? And this equation 7 may be also written as vector L equal to I times vector omega. Here this L has been written at the place of this column vector Lx, Ly, Lz. This is actually the angular momentum vector. And this omega, which is actually the angular velocity vector, that has been written at the place of this column vector or column matrix omega x, omega y, omega z. And this, what is this I? I is actually a transformation matrix. Or you can say that this is such a physical entity that when it is applied on this column vector or column matrix, the angular velocity vector is when operated by this physical entity, we get a physical quantity of different nature. That is L, which is angular momentum vector. Okay, so you can see I have written it here that the equation 8 implies that when I operates on angular velocity vector omega, a physically different vector, the angular momentum vector L, results. I is therefore different physical entity and termed as moment of inertia tensor. This quantity I is termed as moment of inertia tensor. Actually, in matrix form, you can write this inertia tensor I in this way. These are the 9 components of this inertia tensor in 3D space, in Euclidean space. When you talk about Euclidean space, this inertia tensor will have 9 components, and that 9 components have been written as a 3 by 3 array of matrix here. Okay. Now, as you have seen earlier, that Ixy is equal to Iyx. Okay. Similarly, this Ixz is equal to Izx. This Ixy is equal to Iyx. Okay. Iyz is equal to Izy. So this is a symmetric tensor. This is a symmetric tensor. As there the number of components in 3D space of this tensor is 9, so it is a tensor of rank 2. You know, when you raise the rank as a power on the dimension of the space, then you know the number of components. Here dimension of a space is 3, and when 3 will be raised by power 2, then you will get 9. So it is a tensor of second rank, which is also called dyadic. You know, tensor of second rank is called dyadic. Okay. if you have not a concrete idea of tensor or tensor algebra and tensor analysis, I will suggest you watch my videos on tensor analysis in the playlist of mathematical physics of my channel, okay, where you will get all these things in a clear cut way. Okay. Now, the components the inertia tensor and the product of inertia, all these can be now written in a single equation again. And for this, if you consider that this x is now written as x1, y is written as x2, z is written as x3, okay? Then any element of inertia tensor can be written like this: I alpha barabar I beta, and that is equal to this much. Summation over I m I Ri square delta alpha beta minus xi alpha times xi beta. Can you say what is this delta alpha beta? Definitely you have an idea. You have studied it at several places. This is well-known Kronecker delta symbol. And you know, this Kronecker delta is equal to 1 if the two indices alpha and beta are same. But it is 0 when the two indices alpha and beta are not same. So you can check when alpha is equal to beta. Alpha is equal to beta, and that is equal to x, let us say. Okay, or x1 you can say. Then ix, it means x1, you can say, what will be this? This will be then summation I and mi, okay, Ri square. Now, alpha is equal to beta I have taken, so this Kronecker delta will be 1, okay, and minus this will be what? This will be xi square times xi square. This will be xi square. So Rxx we have seen earlier, this is summation over I mi Ri square minus xi square. Okay? But when you will take alpha equal to x and beta equal to y, what will happen? Then you will get Ixy. Can you check it? What will be its value? Here I have taken alpha equal to x and beta equal to y. So alpha and beta are different. And if alpha and beta are different, this Kronecker delta will be 0. So this first term will vanish. And what will be your result? This will be minus summation over I mi. See here. Alpha is x, beta is y. Okay? Alpha is x, beta is y. But x is now x1 and this is in fact y is x2. So this will be x1 times x2. x1 times x2. This will be x1 times x2. Okay? Sorry, here there is no need to write this I. You don't write it. Okay? So this will be this one. And you can check Ixy is given by this expression. You can check it here. Okay? At the place of xi, xyi, I have written actually x1, x2. Okay? Yeah. No, keep I at each. You should keep it. I at each, you should keep it. Then this will be simply I1, I2. Okay? I1, I2. In the similar manner, you can obtain all the components. So this is a very compact equation, very important equation to define all the elements of inertia tensor. Okay? I have written it here. You can see that this Kronecker delta is equal to 1 when alpha is equal to beta, and it is 0 when alpha is not equal to beta. Till now, in our calculation, as I have told you earlier, that we are assuming that our rigid body is composed of discrete particles. But this is not a practical fact. This was just for simplicity of calculation. Actually, in our practical life, we always see most of the rigid bodies having continuous mass distribution. So, what will happen to all these results when we will consider that our rigid body has continuous mass distribution? You know it. When function has discrete values, you know the total value of the function is found by summation. But if the function varies continuously, its total value is obtained by integration. So what we will have to do in case of body of continuous mass distribution, you have only to replace the sign of summation by the sign of integration. And then instead of an ith particle of mass mi, now in case of continuous mass distribution, we will consider a volume element or mass element dm. So mi will be replaced by dm, okay. Summation will be replaced by integration, okay. So in this condition, the matrix element Ixx is defined as integration r square minus x square dm. But you know, if rho is the density of this material or this body at a position r, density, then this density will be equal to dm divided by dv, where dv is the elementary volume at position r. So dm will be equal to rho times dv. So instead of dm, you can write rho times dv. But you know, r square minus x square you have seen earlier, that is equal to y square plus z square. So in this condition, you can obtain the diagonal elements, that is Ixx, Iyy and Izz of these are the diagonal elements. You can see these elements can be obtained using this equation 11, okay. When you have to find Iyy, then at the place of x there will be y. At the place of x there will be y, okay. And in case of Izz here there will be z, okay. Similarly, the off-diagonal element, there are 6 off-diagonal elements, you can see this matrix. And these off-diagonal elements like Ixy is found in this way, minus integral xy dm. There was summation mi now summation has been replaced by integration, mi has been replaced by mass element dm, okay. And at the place of xi, you have to write now xy. Similarly, dm can be written as rho times dv, okay. So in this way, we can find the off-diagonal elements of this inertia tensor, okay. Now again, in general, the matrix element I alpha beta from which you can find both the diagonal elements and the off-diagonal elements, you can use this single equation. By the use of this single equation which I have written in equation 13, you can obtain any element of this inertia tensor or in this matrix. That is, I alpha is written as integral, volume integral of rho of r times r square delta alpha beta minus x alpha x beta. Again you can check, when alpha is equal to beta and that is equal to x, then this Kronecker delta will be 1 and this will be simply r square, okay. And this x alpha, x beta, since you have considered alpha and beta same, so this will be x square, okay. So Ixx will be equal to r square minus x square. Okay. So in this way you can find any element of this inertia tensor by the use of this single equation defined in equation 30. Okay. So this is all about the inertia tensor and the angular momentum of a rigid body. Actually, in our forthcoming video, in continuation of this concept, we will see a very important concept of principal axis, and we will define principal moments of inertia or principal axis transformation we will learn. Okay. And I hope definitely the idea which I have discussed in this lecture definitely you have understand clearly. Okay. Thank you very much.